Are you able to see my screen?
Yeah, it's visible, and also your audio is also very clear. You can.
It's clear. Okay. Yeah. So, hello everyone. Thank you, Professor Sandeep, for introducing me. Um, as he said, I'm Shruti Upadhyaya. I'm working at Cooperative Institute for Mesoscale Meteorological Studies, which is SIMS. So, before starting my presentation, I'd like to talk a few things about my institute. As name suggests, it is a cooperative institute. It means it's a collaboration between NOAA, which is US Department of Commerce Research Center, which focuses on oceanic and atmospheric research, with University of Oklahoma. So we work together with common research interests like meteorology, climate studies, and weather forecasting, other things. So with this, as in my introduction, it is said that I work mainly in algorithm development for precipitation retrieval from satellite data. So considering audience background and everything, I focused my presentation towards applications of satellite-based precipitation, mainly water resources applications. Before starting my presentation, I would like to acknowledge my collaborators and other from Indian Institute of Technology, Bombay, and University of Oklahoma, as well as NOAA. And I would also like to thank principal of this college and HOD and other coordinates for inviting me as a speaker and organizing this webinar series. Thank you. So let's start presentation. So here's how the story starts. First half of the presentation, I will be focusing on introducing satellite precipitation, products, and its background characteristics, and by giving a brief overview of remote sensing. And second half of the presentation, I will be focusing on water resources applications and case studies. So first and foremost question here to answer is why we need satellite for observing precipitation. Conventional method of precipitation measurements are like automatic weather stations or Doppler weather radars. However, the distribution of these are largely limited to land masses. And even across the land mass, the distribution is not uniform. And also, Doppler weather radars are very expensive to maintain. A recent study by Kidd and others in 2017, they say that if you arrange all rain gauges around the world, just one beside the other, it will occupy less than half of the soccer field area. That is how many rain gauges we have all around the world. And Doppler weather radars are mainly in developed countries. Developing countries does not have good network of Doppler weather radars. Especially this figure here shows there are only 13 radars across India, out of which many of them are partly working. Whereas in United States, there are more than 160 radars, and that too they are advanced radars, that is dual polarization radars. However, for applications like near real-time flood forecasting, drought monitoring, large-scale hydrological modeling, crop modeling, weather forecasting, climate studies, we need precipitation estimates at very high spatial and temporal resolution. And this is possible with the satellite data. The importance of satellite lies in these here. That is, it significantly expands the spatial coverage, and most of its data is freely available for the users. This is about why we need to estimate precipitation from satellite. The next question is how we do this. So this may be too much information, but this gives you a background of remote sensing. Mainly, there are two kinds of sensors which we use for precipitation retrieval. One is visible and infrared sensors, second is microwave sensors. So, visible and infrared sensors, waves generally have higher frequency. Because of this, the energy in these waves are higher, and whereas with microwave uh, waves, the frequency is low, whereas wavelength is high, but energy in microwave region is very low. This decides where this sensor should be located in which satellite orbit. There are mainly two kinds of satellite orbits. One is geostationary satellite and second is low Earth orbiting satellite. Geostationary satellite, here the second figure shows at what height they are located. Low Earth orbiting satellite is located at about 850 kilometers above Earth, whereas geostationary satellites are located at very high elevation, that is about 36,000 kilometers high. So, since visible and infrared region of electromagnetic spectrum has higher energy, it can measure or record data at this elevation too. But and they are privileged to be on this geostationary platforms. Whereas microwave sensors, they have very low energy, so they can be only on board this low Earth orbiting platforms. Both has different advantages and limitations. So these two animations here shows how these satellites record data. Low Earth orbiting satellite, as they are, as the name suggests, they are at lower elevation. So they rotate around the world, around the Earth, and they can record only part of the Earth. It cannot continuously monitor the Earth's surface. Therefore, the resolution from this orbits is less. They have lower temporal resolution. Whereas geostationary satellites are in an orbit such that they appear stationary with respect to Earth. That the main advantage here is that they can continuously monitor Earth's surface and they appear stationary with respect to Earth, geostationary. So this is very useful for high temporal resolution applications. But this is about how advantages with respect to data, but what information they capture. You can see here, this small figure here shows what visible and infrared uh, region of electromagnetic spectrum records and what microwave waves record. You can see that visible and infrared waves, since they have lower wavelength, they cannot penetrate deep into the cloud. They mainly record cloud top information. And using this cloud top information, we are trying to retrieve precipitation at the surface. We don't know what is happening in between. So this approach makes it an indirect approach. Whereas microwave radiations, due to higher wavelength, they can penetrate deep into the cloud and we get more physical information from the microwave sensors. So, where does the current operational algorithms focus? They focus on combining these two advantages of both the sensors. One, higher resolution from geostationary satellites and accuracy from microwave satellites. That is how most of the precipitation products are focused. They are combination of both geostationary satellites as well as low Earth orbiting satellites. But most of the research has been focused in last 2 decades is focused on improving microwave based retrievals because we can see more physical information from this. However, the limitation, as I mentioned, is its temporal resolution. But now geostationary satellites, there are new generation geostationary satellites which can measure information at very high resolution as well as more information content is there. So there are new generation of geostationary satellite, and with this there are new opportunities. My research is mainly focused on utilizing this geostationary satellite data And I'm working towards retrieving precipitation algorithms using this geostationary satellite data. So when I started my research, I did some work on analyzing how this geostationary satellites have evolved over time. And this section will give you an idea how important satellite data is and why. This animation here shows how much improvement is there in the temporal resolution. This compares two satellite data from US. One is GOES 13 and GOES 16. GOES 13 had a temporal resolution of 15 minutes, whereas now the latest generation geostationary satellite can record data at every minute scale. This is very important to target uh, to understand and target precipitation processes. Specifically, if you see recently, there has been several events of cloud burst. So if we were able to detect this initialization of this cloud burst, we could have predicted them beforehand. So there comes the importance of temporal resolution, and geostationary satellites help us to do that. Indian geostationary satellites are called INSAT series of geostationary satellites, and temporal resolution of this is 30 minutes. However, India has launched two geostationary satellites at once, and they record at a lag of 15 minutes duration. Therefore, ideally we get satellite images at every 15 minutes across India. Second improvement is coverage. So what I did was I collected data of all geostationary satellites from the beginning when first geostationary satellite was launched. And this figure here shows number of operational geostationary satellites as a function of time. And you can see that compared to 1965 was the when first geostationary satellite was launched, and now we have around 20 geostationary satellites which are operational. This figure here shows where these geostationary satellites are located. Generally, geostationary satellites are located above equator, so there is no latitude information. They are always at 0-degree latitude. The figure here shows x-axis as a longitude, whereas y-axis is not latitude, it is time, which is same as figure A. So here you can see that in 1965, the first satellites, geostationary satellites were launched by USA. Soon, Europe, Japan, and India joined this race. So yes, we are Indians are also one of the pioneers in geostationary technology, and we have almost like 2-3 decades of geostationary satellite data sets. And recently, several other countries such as South Korea, China, and all have launched their own geostationary satellites. So in total, we have 20 geostationary satellites now. Ideally, to have a global record of geostationary satellite, we need just 5 geostationary satellites. But now we have 20 geostationary satellites. And also this data is available at almost like 3.5 to 4 decades, which makes it really valuable for climate studies. For climate studies, we cannot use just 1 year or 2 years of data. You have to analyze trend over decades, at least 3 to 4 decades. Then only you will be able to make comments about climate change. So geostationary satellite data provides this global climate data record, which is really useful. Next, before seeing how much information gain we have from geostationary satellite data, let's see what does these geostationary satellites observe. They observe data, like I mentioned, in visible and infrared region or wavelength regions. So here is the example of 3 channels. Channels, I mean, here is the wavelength region where they record data. First one is visible image. Humans are sensitive to only visible region of electromagnetic spectrum, but there is so much happening beyond this range, and satellite sensors can record this information. So uh, visible images or visible data from satellite, whatever we are getting, it's just like what we see. So whatever we see is captured in the form of image. It's like you're taking a picture, and visible images gives information about visual analysis we can do. Whereas if you go beyond visible region, there is infrared region. So infrared region is mainly sensitive to temperature. So whatever information you're recording in infrared wavelength region, it gives information about the temperature. If there is cloud, it gives cloud top temperature. If there is land, it gives land temperature. If there is no cloud. So infrared region is sensitive to temperature. Whereas the third channel, which is a recent one, is the water vapor region. So we all know that like certain region of wavelengths in electromagnetic spectrum are absorbed in the atmosphere. For example, everybody knows about UV radiation. UV radiation not much reaches the Earth. It is absorbed by ozone layer in the atmosphere. Similarly, there are other molecules in the atmosphere which absorb different wavelength regions. And water vapor is one such region. As name suggests, water vapor channel gives information about the water vapor content in the atmosphere. Although all these three images look same, they give different information. One is visible, as you see visually, it gives that information. Second is about temperature infrared, and water vapor region, it gives information about water vapor content. Higher the water vapor content, brighter it appears in the water vapor image. So actually, I suggest all audience to mute their speakers because I'm hearing so many other noises and it is disturbing me while talking. This figure here shows wavelength of visible and infrared region, which ranges from zero point 0.4 to 14 micrometer, and y-axis shows here percentage of transmission. As I said, some wavelength are absorbed in the atmosphere itself, so you cannot see surface, earth surface at all. So these regions, for example 6 to 7 micrometer, is completely absorbed by water vapor molecules in the atmosphere. So this is really important for remote sensing. Why? Because if you are working in land surface applications where you want to see land, for example, you want to classify land use, land cover. For that, you want to see land. So there should be higher transmission in the atmosphere. Therefore, you will pick those channels or those wavelength region where transmission is high. But since now I am interested in precipitation and atmosphere more, so I am also more interested in this absorption channels too. So another popular region is the water vapor absorption region. So these three channels are very most commonly used channels from geostationary satellites. So this figure here shows how much information growth is there in geostationary satellites, how much technology has grown. So this part B of this figure is same as the one I just showed before, just it is tilted, which is like x-axis shows transmittance and y-axis shows the wavelength. And it also shows different atmospheric molecules which absorbs these wavelengths. And this left figure here shows how many spectral channels were there in and how they have grown over the time. You can see that earlier generation only visible channel was there, and soon infrared channel was also introduced considering its importance. And within a decade, water vapor channel was also introduced, and it is very useful for identifying different types of clouds. And these three channels are called as heritage channels because they are available for over the decades. Whereas if you see recently, there is significant growth in the information content in just last 5 years. We have grown from 3 channels to 16 channels. We record data in 16 channels now. So what does this also says us? This says us that this climate data record is available from one channel of geostationary satellites, but 3 channels, which will help us to analyze more physical processes from this. Here is an example of the 16 channels from GO satellite, which is US geostationary satellites launched by NOAA. I am not going to go in detail about remote sensing, but just to give you an idea what each channel represents and what physical properties they measure. For example, visible region of electromagnetic spectrum is very sensitive. With using this channel, we can identify cloud optical thickness, how thick the cloud is. Generally, it is assumed that thicker the cloud, more rainfall it produces. So we can identify or get this information from visible channel. Similarly, we can get other cloud properties such as effective radius, which is cloud particle size. What is the size of particles within that cloud? So that will help us to retrieve precipitation or intensity of precipitation. Water vapor channels are like there are several water vapor channels in just one absorption band, and each of this channel is sensitive to different level of water vapor in the atmosphere. For example, we can get upper level water vapor content, mid level or lower level, depending on what channel we are using. We can also identify cloud phase. It means whether it is a ice cloud or water cloud. Each of it has its own significance. Using infrared channel, we can get cloud top height. Higher the cloud, it is assumed to be a more precipitating cloud. So using these hypotheses, we can retrieve precipitation using satellite data sets and also analyze more physical or cloud properties using these channels. So this was about my research. I tried to utilize this 16 new generation geostationary satellites and channels and work towards developing new generation of precipitation retrieval algorithms. I'm interested more on studying, understanding and modeling different precipitation processes from geostationary satellite and develop algorithms for precipitation retrieval by utilizing the strengths of this new generation geostationary satellites. And I work with several advanced machine learning techniques. However, as a user point of view, you will not be interested more in knowing about these algorithms. You are more interested in.
Shruti, sorry to disturb you. Sorry to disturb you. I request everyone to please keep your mic off because it is creating a lot of disturbance to her also while she is presenting it. Please keep your mics off because I'm trying continuously to keep your mics off, but frequently one or the other is keeping your mics on.
Thank you, Sandeep.
Hi.
So this was about background of remote sensing, but now we will be focusing more on applications. Before that, I would like you to introduce two different satellite precipitation products where you can get this in data sets, what are its characteristics, and for what applications, what characteristics you should use. Two of the most popular or known products are TMPA3B42 and IMERG. These two are very popular products when you think of precipitation products from satellite data. TMPA3B42 was the first step towards developing merged algorithms after the launch of TRMM satellite. TRMM is the first dedicated precipitation satellite, and it also had a radar on it, so it gives precipitations estimates very accurately. But it is on low Earth orbiting platform, and it has its own limitations. But this TMPA algorithm is developed by combining both geostationary satellites as well as all other low Earth orbiting platform, not just TRMM. Whereas IMERG, TRMM was decommissioned in 2014, and at the same time, new low Earth orbiting satellite was launched, which is called GPM. Yeah, I hear a lot of noises still. Please, can you mute your mics? Okay.
Professor Huggi, no, the organizer can always mute everybody at their level.
No, we are trying, sir. Listen to me, sir. We are trying to mute you all, but still there are some people who keep their mics on.
No. You don't give the facility to everybody. As an organizer, you have an option to unmute everybody.
Yeah, I'm sorry.
Do that. Kindly do that. This is Professor Galgali speaking here.
Yeah, sir.
Yeah. So
We are doing it. We are doing it.
Yeah, it is frequently disturbing the speaker, and she has been requesting, and nobody is listening. So better you do it at your end.
Sir, we are doing it, but there is somebody who keeps their mics on. I am continuously muting them, but still they don't understand it.
No, there is one facility. There is one facility where users or the listeners or the viewers cannot unmute on their own unless the organizer gives permission. Kindly do that.
Okay. Thank you, sir. Thank you very much.
Okay, go ahead.
Okay, after decommissioning of TRMM satellite, another satellite was launched called GPM. It is called Global Precipitation Measurement. And the precipitation product for this is called IMERG, and it is one of the latest, or you can say one of the advanced and latest precipitation product, which is widely used these days. So what things you need to know? Let me give a brief introduction about GPM satellite. GPM was an idea that it is not just one satellite, it is a constellation of satellites. So you can see that several satellites, low Earth orbiting satellites, are rotating around the Earth. And GPM constellation, they collaborated with all space organizations around the world and try to get or bring in together all the data sets and then predict precipitation from this. India also has a satellite here which is called Megatropics. You can see that one satellite is rotating around the equator, and that is Indian satellite called Megatropics, which was launched in collaboration with France. What things you should see when using satellite precipitation products? One is resolution. Spatial and temporal resolution. We can see that earlier generation, that is 3B42, had a spatial resolution of 0.25 degree. 0.25 degree is equivalent to it is equivalent to 25 kilometers, and temporal resolution is 3 hours. It means the satellite precipitation product is available at every 25 kilometers, and it's available at every 3 hours interval. Whereas IMERG, you can see how much improvement is there both in spatial and temporal resolution. IMERG provides data at 0.1 degree Celsius, which is 0.1 degree, which is 10 kilometers, and temporal resolution has improved from 3 hours to 30 minutes. Because of this improvement is mainly because of improvement in constellations of low Earth orbiting platforms. Other things, what do you see? These you can also see that these products are available from 1998 or 2000 till present. So they are available and they are at global scale. And to download these data, I have provided the links here. If not, you can directly search this product name in Google and you will find a download link. These two products are developed by NASA. Other important thing you should know about precipitation products is its latency. What does latency mean? Latency means when the product is made available to the users. Suppose, for example, you're working on applications like real-time applications like flood forecasting. You need precipitation estimates as soon as possible so that you can run your flood prediction model. For that, you're more interested in getting precipitation estimates at real-time basis more than accuracy of these products. So these you should, for that such applications, you should look for products with lower latency time, and these products are generally called as real-time products. So both TRMM and IMERG has a real-time product which is 8 hours. They also have another product called research product, which is available after 2 or 3.5 months. Here, they use other sources of information such as rain gauges or other radar data wherever available to improve the retrievals from satellite data. So they are correcting this satellite data using rain gauges and other sources of information. But to collect all this information around the world and to apply the algorithm and get the precipitation, it takes time, and therefore they have higher latency. If you're looking for accuracy, you should focus on using research products, or if you're working on real-time applications, you should focus on using real-time products. So latency is one of the important component of any precipitation products. These two products, as I said, TRM 3B42 and IMERG, are from NASA, but other space organizations around the world also have their own merged products. Some of them, like for example, GISMAP is launched by NASA and it has its own characteristics. Although all of them use similar data set, the way in which they process data, they build algorithms are different, and that's how the accuracy varies from region to region. Apart from 3B42 and IMERG, GISMORPH, CMORPH, and Persian CCS are other popular precipitation products, and you can download these data from these links. Another category of precipitation product are reanalysis product, or you can say this CHIRPS, GISMAP, and GPCP and MSWEP. These three products are developed mainly for climatic applications. It means they are more focused on getting most accurate precipitation rates and for longer period of time, and it should be consistent over the time period so that you can do climate scale analysis. So these three products, although they are available at very latency period is very high, but accuracy of these products are very high. So you can use these products for if you are not working in real-time applications, and they are very accurate and consistent, and they are available for at least 3 decades of data. And global, you can do studies at global scale to country scale. India also has its own precipitation products, and it has two algorithms. One is called IMSRA product and second one is called hydro estimator, and both of them are available at native resolution of Indian satellite, which is 8 kilometer and half an hour scale. The coverage is also, you can see it's mainly over Indian region. And you can freely get this data from Indian website called MOSTAC, which is maintained by Space Application Center, SAC, from ISRO. So you just have to register there and you can download this data sets from MOSTAC website. So this was about, till now I have discussed about remote sensing, what information we capture from satellite data and how we use that information for retrieving precipitation, and what kind of products are available, what are its characteristics, and from where we can get these data sets. Now we will move on to applications of these satellite-based products. So what I did is here I prepared a summary table from several articles, and I tried to summarize and bring you the different applications of satellite-based precipitation products. First area here is extreme. Okay, let me introduce this table where first column gives the broad area, second column gives the specific applications for which the satellite products are used, and how this product is used, and last column gives the references. If you are interested in any particular applications, you can go to these articles and then understand how they have done and try to replicate for your area. So, first and foremost important application is extreme events and disasters. Floods, landslides, cyclones, and hurricanes are the most extreme events which is affecting many people. So, for that, for flood models, landslide prediction, and cyclones, precipitation is one of the important forcing variable, or I can say it is one of the important input for these models. And several studies have showed that we can use satellite-based precipitation products to improve these predictions. Specifically, near real-time flood forecasting, which I have been highlighting from the beginning of my presentation, satellite is the key source for near real-time flood forecasting, and you can do this study at global scale. Agriculture and water resources applications like drought, water management studies, and famine early warning, all of this can be done with satellite precipitations. After this slide, I will be discussing few case studies where I have been collaborating with other people from my lab and try to utilize the satellite products for different applications. I will show you few case studies among these. The third category is weather and climate applications, numerical weather prediction models, land surface modeling, and even aerosol and atmospheric chemistry. All of this requires precipitation as important forcing, and they work at global scale to regional scale. Another very recent application of precipitation and very interesting is satellite precipitation products are also used for disease tracking and animal migration tracking. Several studies used satellite precipitation products to track malaria and other epidemic diseases. And currently we are also trying to work in utilizing satellite precipitation product and find if there is relationship between weather parameters and COVID-19 spread, etc. So if you are interested in ecology and other health application, there are studies, very preliminary, they are in starting stage, but there are several studies now. So let's move to case studies. First case study I will be talking is about drought monitoring, which is at a country scale. Here, we have worked, our objective was to evaluate if we can use satellite-based precipitation products for drought monitoring applications. And meteorological drought requires, or I can say one of the main input for meteorological drought analysis is precipitation. And here in this study, we have used CHIRPS product because it is available for longer period of time, and we wanted to do drought analysis or drought monitoring for over decades. And also CHIRPS product is proved to be very accurate over our study area, which is Ethiopia. So how do we monitor drought is by using drought indices, which are very well established indices. For this study, we selected two very popular drought indexes, that is effective drought index and standardized precipitation index. What these drought indices gives us? So effective drought index is we picked this mainly because it takes into account the previous precipitation events. So it gives a more advanced drought index, whereas SPI is very basic index, but it is recommended by World Meteorological Organization. So we tried to compare both the indices. So what these indices gives, what is the meaning of these indices? It generally gives how much precipitation is deviated from its long-term mean. So this table here shows what are the values of these drought indices, and if that is the value, in what drought category they falls. So if anomaly is towards negative, that is precipitation is less than long-term mean, then there is a drought. So negative values of these indices are generally related to drought. And how much negative value shows how much severe the drought is, whether it is mild drought, moderate drought, severe drought, or extreme drought. This is just a background of drought analysis. But our main, this is already well established. Our idea was to evaluate if we can use satellite precipitation products instead of gauge data here. So our study area is Ethiopia, which is a country in eastern side of Africa. We have done several analyses like intercomparing different climate regions, taking into account seasonality and everything. But for now, I will be focusing on just highlighting whether we can use or not. So for that, I'm showing you just one of our results, which is EDI drought index for March month as a function of time. Here, we have selected 3 years in which 2 are drought years, 1984 and 2011 are drought years, whereas 2007 is non-drought year. So here we can see that the gray marked regions are drought years, whereas blue is non-drought. For drought years, you can see that EDI values is negative, which is derived from satellite precipitation product, whereas for 2008, which is a non-drought year, EDI value is positive. And you can also find the level of severity of these droughts. 2011 event was more severe compared to 1984 event. So this shows that we can use satellite precipitation product for drought monitoring application. But there are several advantages of using satellite precipitation products than gauge products. That is spatial analysis. This spatial analysis will be very important. For example, applications for crop insurance. They want to know whether specific region is affected by flood or drought. You cannot just say, okay, this entire city is affected by drought. That is not the case. But by using satellite data, you will be able to do spatial analysis of that. You can say, like within one basin here, we have shown this 3 basin, which is Shabela, Rift Valley, and Ganela. So these 3 river basins, within this river basin, there is so much variation in drought indices. So this we were able to analyze because we are using satellite products and not the gauge data, which is just a point data. So second application is very recent study where the objective was to evaluate if IMERG, which is the latest NASA's precipitation product, whether it can capture Indian monsoon characteristics or not. So as you all know, monsoon hits India, or onset of monsoon is on June 1st, and withdrawal starts from September 1st. So June to September is the active monsoon season in India, whereas remaining other months are considered to be the dry season. So in this study, the study area is marked here in this gray highlighted region, and precipitation is analyzed for over 2 or 3 years of time. The second figure here shows IMERG precipitation as a function of time. X-axis is a time and y-axis is latitude. Across each longitude, the precipitation rates are averaged here. So just it is given as a function of latitude. You can, the colored regions here shows the precipitation rates, which bar is given here. You can see how much precipitation is there. And non-colored region is the dry season. You can see that IMERG is able to capture well exactly the onset of monsoon, that is June 1st, and also withdrawal of monsoon. The dotted lines here shows the mean mean monsoon characteristics or mean precipitation rates. And IMERG is able to capture that, and it also able to capture dry seasons well. And here we can see 2 extreme events. One is one highlighted here is the tropical cyclone Hudhud, and this one highlighted one is the tropical cyclone Romao. So this shows that we can use satellite precipitation products for using weather analysis or even climate studies. The third case study is flood forecasting. Here I am trying to highlight studies like country scale study to global scale study, which we are able to do only because of global scale precipitation products, which is available from satellite products. So here I am showing an example of global flood forecasting model, which is developed at University of Oklahoma by my research team. And you can even download this flood forecasting data at floods.global, and you can use it for your analysis. So the objective was to develop a global scale flood forecasting system. For that, for predicting stream flows, and for that, we are using a framework or hydrological model called EF5, which is also developed at OU. It is a distributed hydrological model, ensemble hydrological model. The rainfall forcing or precipitation forcing for this models are NASA's GPM IMERG, which I have been highlighting from this presentation from the beginning. And for forecasting, we use GFS forecast, which is a precipitation forecast available globally. So if anybody is interested, you can go to this floods.global and analyze flood models. Here I have given one example of recent flood. I don't say recent, it is last year's flood event, which is 8th August. We can see that there was a flood in Gujarat and Maharashtra near Mumbai. So with this flood model, they were able to predict this well before. And you can see that there is very high stream flow or runoff over this region. So we have seen applications from country scale to global scale, but you can do analysis at watershed scale or even at finer scale at smaller regions too. The fourth case study I'm showing here was to highlight that there can be different applications other than water applications, and this application is focused on crop modeling. Here also the objective was to evaluate if we can use satellite-based precipitation products for crop modeling. The study area is two small regions in Western Africa, one in Nigeria and one in Benin. The crop model used is Sarah H. I'm not very confident about talking about crop models, but if anybody is interested in more learning of crop models and about Sarah H, they can go to this link. So here the objective was they compared different satellite precipitation products for crop modeling, and they analyzed which is the best product they can use for crop modeling over this region. So the figure here is just one result from their study. It is not a recent one. This is a little old study which is done in 2013. So they do not have IMERG precipitation product for evaluation. They have TRMM 3B42, GPCP, GIS MAPC, MORPH, and 3B42 real-time product. They have also evaluated the research product, both the products as well as Persian. So I have discussed about all these products just a few minutes back. So the figure here shows what is the bias in yield, that is error in yield for different precipitation products. What they notice is that if satellite products are not corrected with gauge data, and if you are using near real-time products, there is a large error, which is expected because they are quantitatively, they are not very accurate. But if you want to know when and where extreme events can occur, for that, real-time products are really useful. And they find that TRMM 3B42 product is the most accurate one, which least bias. So they can say that the bias is almost close to zero, and we can replace gauge data with satellite-based precipitation. So these are all different applications we have seen. With this, I would like to conclude my presentation by highlighting key takeaway points. So So we have seen that there are several new generation satellites such as NASA's GPM and NOAA's GOSAR, and they provide unprecedented and highly at very high spatial and temporal resolution global precipitation products. And most important thing is all of these products are freely available for user community. And by describing several applications and at different scales, I have shown that these products are useful for several applications. And I can all these studies I have shown are almost like recent last few years of studies. So this shows that this is a recent or a trending work, like utilizing different remotely sensed products for applications. And as I mentioned, these are available at global scale. So this allows us to go from regional scale to global scale applications like flood, drought, and landslides, which we have been modeling at watershed scale. But still, if you go at finer spatial and temporal scale, as I highlighted, near real-time precipitation products have large bias and uncertainties in them, and still algorithm developers like us are working hard towards improving these precipitation products. With this, I'd like to say thank you for giving me this opportunities, and I'm happy to take questions. And if I'm not able to answer any questions, I can reach me out at my email address, which I have given here. Thank you.
So we are opening up for the questions that will be asked by the participants. If there is anyone who would like to ask question, you can ask the question either in the chat section. We'll read out the question, or you can keep your mic on individually.
Hello. Hello.
Yes,
Hello.
please introduce yourself.
Yeah, this is Dr. Chowdhury from University of Mumbai. Ma'am, very nice lecture and lecture was very informative. Thank you for that. I wanted to ask you that can you share your PPT with us?
Yes, of course, I can share. I will be sharing with Professor Sandeep, so he can share with you all. Yeah.
And ma'am, can we compare this? Can we use this data for climate change modeling for future scenario?
Yes, there are several studies, and as I highlighted, you should be focusing on using research products or reanalysis products, which are considered to be very accurate for climate scale modeling.
But ma'am, the rainfall is based on various factors. See, if we are doing climate change modeling, the result will be very good regarding temperature variable. But what about the rainfall? Because of we cannot predict that much of rainfall based because of these are based on the various variable. So what is the reliability of the future predicted rainfall?
Yeah, there are several studies, and in my lab itself, we have been doing studies like uh, precipitation is considered to be one of the most highly variable and most difficult thing to model. So
Yes.
climate models are considered to be very weak in predicting precipitation, but they are good in predicting temperature, humidity, and other things because they don't vary spatially much. So what we
Yeah.
are trying to do is either assimilate satellite data set in weather prediction model so that we can predict precipitation in a better way. We are still working towards that, and most of numerical weather prediction models now are trying to use geostationary satellites to assimilate. Assimilate, I mean, in real-time basis, whenever satellite data is available, we use that. Then we try to predict precipitation. Other way, like when you are as a user and when you are trying to use this prediction model, you can do bias corrections or other statistical downscaling or other dynamical downscaling models are available, which you can use and use variables like you said temperature, which are predicted well by weather prediction models, and you can relate that with precipitation and improve precipitation prediction. That is what is happening in research for now, because precipitation is considered to be the most difficult thing to predict.
Yeah, ma'am. And
Okay, okay.
another
Sir,
question is
we'll go
that.
to the next question. There are other questions. There are other asking the questions. So we'd like to go to the next person. Anyway, contact her on our mail also if you have any further doubts. Okay. So we'd like to go to the next question, which is Sujata has asked this question. How can we use the application on soil?
So soil is totally different domain, but there are satellite products for to estimate soil moisture. So you can focus on using those products which are based on soil moisture. But for hydrological modeling, like in my research lab, we are working towards assimilating both satellite precipitation products as well as satellite soil moisture products with hydrological models, so that we can improve hydrological predictions with that. So I think that's how I can answer your question.
There is another question. Does resolution of satellite data has importance in flood mapping? If so, what resolution we should use?
So yeah, of course, it depends on what model you are using. If it is distributed model, yes, resolution plays a very important role. But if it is lumped model, I don't think you will be interested in using satellite precipitation, because you just need a average precipitation for the area. But yeah, when you are using distributed model, always higher the resolution, it is better. You can do fine scale modeling. So the best resolution available for flood forecasting is, as I said, from Indian satellite, its resolution is 8 kilometers. And if you go for satellites like which are in US, which are highly advanced, you can get precipitation estimates as fine as 2 kilometer scale.
I would like to ask another question from Abhishek. Is it necessary to validate the satellite rainfall data sets before its application?
Yes, it is always recommended to validate satellite precipitation products, because several studies have showed that different products perform differently in different regions. So, for example, I have done myself one study comparing different satellite precipitation products across India, and I noticed that in Western Ghats, most of this precipitation product underestimates this heavy rainfall. Whereas when you go towards leeward side, like Bijapur, it is located in the leeward side of this region. So we receive less precipitation. And this sudden variation in precipitation is slightly like weakly captured in satellite products. And therefore, to use at regional scale, it is always recommended to compare different products and see which one is performing best over your region.
Okay. So there is another question. I think you, while explaining the application, you would have explained this, but there is the same question. How can we use this in the field of health and disease? Like basic.
Yeah. Yes. So in the health and disease, for example, okay, I will talk in terms of health and disease. So there is recently one study on malaria. You can think practically that wherever there is higher precipitation, there will be more mosquitoes in that region. So you can say this is correlated with the malaria cases in that region. So in that way, you can try to model precipitation with health or diseases. This is just one example, but there are several other applications too.
So another question from Rajsekhar. For drought analysis using real-time satellite data leads to uncertainties. How do you deal?
Um, I think for drought analysis, if drought analysis is such applications where you are not looking at very fine scale. Drought does not happen in a one day. It is a cumulative process. And for that, satellite products are shown to be very good. I don't think so. There are much uncertainties with drought prediction and satellite products. But yes, for flood modeling, there are several uncertainties because you are using real-time products.
There is another question. I guess this is the last question. Can we use satellite precipitation data to generate IDF curves?
Yes, of course, you can use satellite, and good thing will be you can produce IDF curves spatially too. That is one of the advantage which I have been highlighting all my presentation.
So if there are any further questions, you can write in the chat section. So I'll ask the our speaker. If at all you want to discuss her privately, you can mail her the difficulties that you find.
Yes, of course, you can reach me out as I show my email. You can reach me out anytime. So,
Okay, there is another question that we have. Is it okay? We'll continue this question tree, or we'll.
yeah, it's fine, totally fine.
Okay. The speaker has the time. If you want to ask further question, you can ask. There is another question that has come up from Nagaraj Patil. What is the resolution of satellite data of PCP? Which product?
Are you talking about GPCP? If so, GPCP is very coarse resolution. It is available at so it is available at 2.5 degree, which is 250 kilometers. Yes, 250 kilometers. So which is very coarser scale. But GPCP is mostly used for climate studies, not for other studies. So coarser scale resolution does not matter much.
So please introduce yourself and then you ask the question. Which product is fine resolution and product? The same person is asking this question. Which product is asking?
Yeah, IMERG is one of the most latest generation and finest resolution product available now. If you are looking at global scale, yeah, it is at 10 kilometer by 10 kilometer spatial resolution and 30 minutes temporal resolution.
So another question, how can doing a comparison between PRMM and GSMAP rainfall data sets without any ground data?
Okay, this is a challenging question because we need some reference for evaluation. If you are working in Indian region, I say there is a lot of gauge stations, regional gauge station, at least you can get one or two gauge station data, or there is a global gridded gauge data provided by Indian Meteorological Department, which is at daily scale. So you can evaluate these products at daily scale. If none of this is available, it is really challenging to say how accurate precipitation product is. And recently, like very recently, last 2-3 years, we have been working towards developing techniques to evaluate this product without any reference data. Like there are techniques like triangulation, for example, in surveying we use, right? So similar way, similar techniques have been developed without any reference. We can uh, use create ensemble products or develop but this is still under development. I'm not sure if it is publicly available or you can use it, but I suggest to use at least one gauge station to validate it.
Okay, thank you very much. I guess all the questions are completed. There are no further questions. Thank you very much for
Thank you.
joining, giving us a brief understanding of the remote sensing. There are several points from your presentation. I'm very happy to have you as in person also. Thank you.
Thank you. Yeah, if anybody has more questions, they can reach me out through email. Thank you.
Thank you very much.
Excuse me.
Yes, who is this? Please introduce yourself.
Ma'am, what is the process in drought analysis? What is the actual process involved?
This question has already been answered, so there is no need to answer on this. Yes.
Madam, last question, huh? Madam, please.
Yeah.
Madam, which is the open source software which is used for the drought modeling?
It's so drought monitoring. These are just indices, small indices, which you can implement even in Excel too. It is just that small process, and we are working using MATLAB or Python or R, these open source softwares.
Okay.
MATLAB is not open source, but R and Python are, so you can use those two.
Okay. If you have any Excel files, can you share with us?
No, I don't have Excel files because these are large scale and we are working on Ethiopia, not India. So
Okay.
yeah, I'm sorry for
Thank
that.
Thank you, madam. Thank you.
Thank you very much, Shruti.
Thank you.
Joining.
Yes, see you.
We are ending the session. We'll come back at 3 o'clock. So we will send you the of the next session also through WhatsApp. We'll send this message so you can come at 3 o'clock again. Thank you for all joining.
Yeah.